Hello, in this video we're going to go over the extreme value theorem. The extreme value theorem guarantees the existence of a maximum and a minimum for a function that is continuous over a closed and bounded interval. But first, the definition of maximum and minimum. We say a function f from d to r attains its maximum at x0 if f of x0 is larger than or equal to every other value of f. And x0 is called a minimizer for f. Similarly, we define minimum and minimizer. So let's first start with an example of a function that is continuous, but it does not have a maximum or a minimum. Consider the function f of x equals 1 over x, and I'm going to draw the diagram on the right from 0 to 1. So it starts from 1 from the right, if we draw it from the right, and it is a hyperbola. As you see, the value of the function goes to infinity as x approaches 0, which is why it doesn't have a maximum. And there is also no minimum because the values approach 1, but they never reach 1. In other words, there's an infimum for the image of the function, but the infimum is not in the image. So we are going to prove it does not have a maximum or a minimum value. Since we are trying to prove negatives, we are going to use proof by contradiction. So on the contrary, assume x0 in 0, 1 is a minimizer. So I'm taking some value on the inside the interval 0 to 1, and I'm assuming that this is the smallest value. So if that were to be the smallest value, it would mean this would have to be the smallest value. However, if we go a little bit to the right but stay below 1, then we would stay inside the interval 0 to 1, and the functional value is going to become even smaller. So now we have this 1 plus x0 over 2. So that's the average of 1 and x0. That's greater than 0 because 1 and x0 are both positive, and it's less than 1 plus 1 over 2, which is 1. So that means 1 plus x0 over 2 is inside the interval from 0 to 1. Now if we look at f of this number, we get 2 over 1 plus x0. And this quantity, we are going to argue that that is less than f of x0. This is less than 2 over. We are going to replace 1 with x0. Since 1 is more than x0 and we are dealing with positive numbers in the denominator, the fraction becomes larger. So decreasing the denominator increases the fraction. So that gives us 1 over x0, which is f of x0. And this means x0 is not a minimizer. Now we are going to show that it does not have a maximum. So again, assume on the contrary, assume that x1 is a maximizer for f. Now, if I take a number that is a maximizer for this function, then I can of course create things that are higher than that. All I need to do is to take something between 0 and x1. So x1 over 2 is positive and is less than 1, which means if I look at f of x1 over 2, I would get 2 over x1, which is more than 1 over x1, and that's f of x1. So that means x1 is not a maximizer for f. So this completes the proof. So we showed that this function, even though it is a continuous function, it doesn't attain its maximum. nor does it attain its minimum. And if we think about this function is a rational function. It's a polynomial over polynomial, which is why it's a continuous function. Now, the big theorem that we're going to prove today is the extreme value theorem. And here's the statement of the theorem. It says any continuous function on a closed and bounded interval attains both a maximum and a minimum value. So let me start with naming the function and its domain, and then we'll go over the proof. So suppose f, so it's over a closed and bounded interval. Suppose this is continuous. We would like to show that there is a maximum for this function. So how do we show that there is a maximum for a set? So let's call the set the image of this function S. So let S be the set of all f of x such that x is in the domain of this function. What we would like to do is that this S has a maximum value, and we can also show there is a minimum value for the image, but we will only show the maximum, and the minimum would be similar. We'll talk about that at the end. So if you look at the image of this function, we want to show this set S has a maximum, and this maximum, it means it is f of some value in the domain, f of some number a0 inside ab. In order to show a set has a maximum, we need to show first it has a supremum, and second, the supremum is in the set. So these are the two things we need to show. So how do we show there is a supremum for a set? If we step back and think about how we show the existence of a supremum, this is something we talked about the very early on in the class, which is in order to show a set has a supremum, we need to show the set is non-empty and bounded above. It has an upper bound and it is non-empty. If a set is non-empty and it has an upper bound, then the completeness axiom tells us that it would have a maximum, it would have a supremum. So let's just start with that. So clearly this set is non-empty. For example, f of a is in S. So that tells us that S is non-empty. Now we would like to show that this S is in fact bounded above. Let's assume S is not bounded above. We will prove S is bounded above. Suppose on the contrary it is not. So that means every number that you take, there is something in this set that is larger than that. So for every natural number, there is something in that set, let's call that f of xn. There is some xn inside AB such that f of xn is more than n. Now, what we would like to do is we would like to use the continuity of the function f and get a contradiction. However, how do we use continuity? If we think about the continuity, the definition of continuity, we need a sequence that is convergent, and then we can deduce that f of that sequence converges to f of the limit of that sequence. We need a sequence that is convergent. The sequence xn is not a convergent sequence, or at least we don't know that it is a convergent sequence. So think about whether you can actually find a sequence, extract a sequence that is convergent. So how do we deal with sequences that are inside a closed interval? Can can we extract some sequence that is convergent? And the answer is yes. The answer is we can use the sequential compactness theorem. So by the sequential compactness theorem, there is a subsequence, let's call that x sub nk, such that x sub nk converges to some c, for some c inside interval ab, because the closed interval from a to b is a sequentially compact set, which means every sequence inside AB has a subsequence that converges to something in AB. Since f is continuous at C, f of x and k converges to f of c. Now, f of x and k is a convergent sequence, which means it would have to be bounded. Therefore, f of x and k is bounded. But this would violate the fact that f of xn is greater than n. How so? Suppose f of x and k is less than some number a. We know this is for all k. We know that there's an integer more than a. So by the Archimedean property, there is some positive integer such that a is less than m. So this means f of x and k is less than m for all k. However, if you look at f of x sub nm, this is greater than n sub m. And this was because of, I would call it star perhaps, what I have up here. I call this star. So that means m is more than n sub m. But that is not the case, because I'll explain why there is a contradiction. Because if you look at n sub m is at least the mth positive integer. So it cannot be less than m. So this is a contradiction. And this shows S is bounded above. So again, going back and seeing what we did, we assumed S is not bounded above. We created a sequence using the definition of not bounded above. We used sequential compactness theorem, then applied continuity, then we used the fact that convergent sequences are bounded, and then we got a contradiction, which means S is in fact bounded above. Now, since S is bounded above and it is non-empty, there is a supremum. So by the completeness axiom, let me call that S. S equals supremum of S exists. Now that there's a supremum, we would have to show this supremum is in fact in the set. So we will show S is in fact in S. And if we show the supremum is in the S, it means there is a maximum. Okay, so let's see how we can do that. If we take S, we can create a sequence that approaches S inside S. So if I take S minus 1 over n, I can get a sequence of functional values, f of perhaps a n, that approaches S. Then I would again apply sequential compactness theorem and continuity. So let's go from there. So for every positive integer n, since s minus 1 over n is less than s minus 1 over n is not an upper bound for capital S. Thus, there is some an inside a to b such that s minus 1 over n is less than f of an. And of course, this is always less than or equal to s because s is the supremum. So this means the distance between f of an and s is less than 1 over n. By the comparison lemma, limit of f of an is in fact s as n approaches infinity. So f of an approaches n because, let me be a bit more clear, 1 over n in fact approaches 0. So 1 over n approaches 0, therefore f of an must approach s. If I can show that an is a convergence sequence, then f of an would approach f of the limit of an, and that would mean s must be f of limit of an. However, an may or may not converge. So here we're going to use the sequential compactness theorem. By the sequential compactness theorem, there is a subsequence a sub nk of an that converges to some r inside ab. Since f is continuous at r, limit of f of a sub nk is f of r as k approaches infinity. Now, if you look at this star, by star, since f of an approaches s, f of ank approaches s as well, because if a sequence converges to a number, any subsequence of that also converges to the same number. And then by uniqueness of limit, f of r must be s, and that is why s has a maximum value. So we showed that if you have a function, continuous function, over a closed and bounded interval, then its maximum will be obtained. Now, the same thing is true for minimum. To prove the theorem for minimum, apply the result we found above to minus f. So this would have to be written, but the idea is we know negative f would have a maximum, and then argue that that maximum, if you negate that, would be the minimum for f. Okay, so the last thing we're going to do today is an example on finding maximum and minimum values of a function. Keep in mind that existence of a maximum and minimum was proved in the extreme value theorem, but no algorithm was given for finding that maximum or minimum. It was a very existential proof. It didn't give us a roadmap to find the maximum and minimum. that is something that we will build. You have seen the tools in calculus, single variable calculus, and we will build these tools later on in the course when we talk about derivatives. So we have this function x squared minus 2x, and we want to find the maximum and minimum of this function. We know there is a maximum and minimum, but we don't know exactly what it is. So in order to find the maximum and minimum, we would have to use some algebra. We are going to complete the square and then see whether we can bound this function by two numbers and then show that those two numbers are in fact functional values. So if you take x between 0 and 2, which is the domain of this function, then x minus 1 would be between 1 and negative 1. X minus 1 squared is between 1 and 0. Keep in mind that I cannot square both sides of this. I have to take cases of when x is positive and when x is negative. When x is positive, x minus 1 is positive, x minus 1 squared is less than 1. When x minus 1 is negative, x minus 1 squared is still less than 1, because when you square both sides of an inequality, when both sides are negative, you have to flip the direction of inequality. And by the way, these have equality signs. And this means if I subtract if I subtract 1 from all three sides, I would get f of x is between negative 1 and 0. So for every x inside the interval, f of x is between negative 1 and 0. Furthermore, we can obtain 0 and negative 1. For example, if you plug in f of 1, you get negative 1, and f of 0 gives us 0. Thus, negative 1 is the minimum and 0 is the maximum of this function f. And that brings us to the end of this video. If you enjoyed this video and you want to continue with this class, feel free to subscribe to be able to see the later videos. I will see you in the next video.